Okay, thank you, Diane, and thank you to the organizers, so Martin, Okay. Okay, so it's great to be here. I was a postdoc here 13 years ago, so it's good to see that. So as Diane said, my talk is about a classical question, namely counting the number of tritangent planes in the space Sextic complex first. And we're going to use the tropical approach to do this, and use classical results, and then move on to what happens over other things. So the first part of the talk is supposed to be a survey on the subfield. So I'm going to talk about tropical geometry. And I basically try to see who else is speaking about tropical stuff, and I try to give some basics so that other talks will be hopefully easier to understand. And let's go from there. And my apologies if you already know all this. So first, natural question: what is tropical geometry? So for now, we're going to think of tropical geometry as a tool that turns algebraic geometry questions or objects into combinatorial objects. Geometry and combinatorics. And there's going to be a map that's going to be called a tropicalization map. And of course, the natural thing to do is to try to do something on the tropical side and try to see what do we learn from the combinatorics about an algebraic geometry question. Okay, so that's going to be sort of the flavor of this talk and some other talks. For example, Heidis is going to talk about bitangents to plane vortex. Sabrina is going to tell us about other fields, quadratically rich fields, and some enumerated questions you can do on this side and learn about the enumerative geometry. So the classical question. And there's a lot of free talks, I think, the small talks that also deal with more of how can we sort of enrich the tropical thing with some more structure, like a scheme structure. And then, for example, Claudia Yun is going to tell us something about topology of moduli spaces of objects on this side, and the hope is that some of the topology can be translated back to here. Okay, so we're going to have cohomological approach questions that can be answered through the combinatorics. If there's some other talk, I apologize. This is what I remember from. Okay, so the main idea, so let me write down the two slogans. So the slogan 1 is that tropical geometry is geometry over a semi-field over the tropical semi-ring field. Field is going to be R bar, which is going to be R union minus infinity. I'm going to have a funny addition, which is going to be the max between two numbers, and then a funny multiplication, which is the usual addition. There's always this discussion about max versus min convention. Because I'm going to draw some stuff, for me it's easier to consider the max, but both are valid and should be considered together. Okay, so that's slogan 1. My slogan 2 will be tropical varieties are combinatorial shadows over, of algebraic varieties are valued fields. So fields that for today, the example you should have in mind, maybe two examples you should have in mind. I'm going to consider algebraically closed fields, and I'm going to, my example, well, it's going to be, I'm going to take the field of Laurent series with the t-valuation, and I'm going to consider its algebraic closure. This is just going to be what is known as the Fizeau series field, and that's just, we're going to work with Laurent series, but not in T, but in T over to the power 1 over n, and I'm going to let that n vary. So my evaluation is the lowest order in T that you can consider. Okay. Another example, if you like number theory, it's going to be QP bar with the periodic valuation. My examples are going to be on this field, but so I'm not going to really dive more into this periodic stuff. Okay, so again, we're supposed to tropicalize things, so let me let's go back to the table. So we have algebraic geometry versus combinatorics. And so we're going to do two things. We're going to tropicalize points. And because we're working with valued fields, I don't want to have infinities floating around. So my points are going to be in torus, n-dimensional torus. So these are going to become now points and what I'm going to do is I'm just going to take a couple, x1 to xn, and I'm going to map it to the negative of the valuation of the first power series and going all the way to the negative valuation of the last power series. Okay, so that's how we tropicalize a point. Now, let me go back to this one. Yeah, that's not going to work. Now, a polynomial, we're trying to do algebraic geometry, so we have solutions to polynomial systems. So how do we build a tropical polynomial? Well, we're going to take a classical polynomial. So I'm going to have a sum of coefficients, and then we're going to have x1 to some power, all the way up to xn to some power alpha n. And remember, I had my tropical sigma field that turned sums into max and products into standard addition. And then I have a coefficient, so this guy lives in K. And so what I'm going to do is I'm going to replace that number by the negative of its valuation. So the tropical polynomial now is going to be a max over alpha. And we say A alpha different from 0. And I'm going to have minus valuation of A alpha plus alpha 1 x1 plus alpha n. So if you forget about the max, and let's say we had just one monomial here, this is going to become an affine linear linear map from Rn. So I can plug in any x I want, and I'm going to get a number back. and it's going to have integer slopes just because these alphas are integers. Okay. Now, if I have a max, this is going to be a piecewise linear thing. So if I take a random value of x, this guy, this max is going to be a thing exactly for one of these terms. So I'm going to have a linear thing. But if my x's start to be special, then maybe two of these guys have the same value, and I realize it's the max, I'm going to have piecewise linear things. So from f, we're going to go to top f, which is a piecewise linear map Rn. Okay. Good. So let me just give an example. I will have f e to the 1/2 plus t cubed times x squared plus 2yz. So then the topical polynomial evaluated at x, y, z. And let's remember this is a point in R3, whereas these guys are supposed to be, choices of Cueto series. If I want to find solutions to these guys, x, y, and z are going to be Cueto series. So this is going to become the max. I have to replace the coefficient, replace it by the negative of the valuation. So I'm going to have minus 1/2. Then I'm going to have 2x. And then for the second term, the 2 has valuation 0. And then I'm going to have plus y plus z. Okay. Great. So now the question is, well, I know how to tropicalize points. I know how to tropicalize polynomials. What happens with varieties, right? So I'm going to write it here. For tropical varieties. Well, there's basically a theorem / definition for these things. It basically says you can do two things. You can think of a variety defined by an ideal. So I can do two things. I can look at solutions or points in this variety, and I can just take coordinate-wise negative evaluation. So that will be one definition. So I'm going to take prop E. This is going to be the negative evaluation, one negative evaluation over sense. If I take a point in my variety, so this, if I take, for example, things in Cueto series, I'm going to just have points that have rational entries, right? Because all my exponents in my Cueto series are rational. So I would like to have something that is sort of connected. So I'm going to take the closure of this inside R. Okay, so there, I'm going to take the points, I'm going to take the Euclidean closure, and that's going to be my set. So that's one approach, using the thing over points. Now, if you think about solutions to these things, well, if there's going to be a solution to this polynomial, well, what are the possible values of the valuation of x, valuation of y, valuation of z? Well, if these guys have different valuation, then there's not going to be able to, we're not going to be able to cancel the lowest term, right? So there should be something about valuation of this term compared to valuation of that guy, and that's precisely saying these two guys should agree. Okay, and so here, the tropicalization of the variety defined by some polynomial is going to be the corner locus of f in Rn. I'll draw a picture in a minute. And so if I have more than one polynomial, well, I can just take solutions every possible polynomial in my ideal and intersect everything. So the second definition will be I take any f in my ideal, and I'm going to take the product over any defined by the corner locus of this tropical polynomial. And of course, in principle, this is an infinite intersection, but it can be made finite. You might need more than just the generators of your ideal, but you can take finitely many of these things. So if you think about what's going on, corner locus of these things are going to be, you're intersecting a bunch of affine hyperplanes, and then these things should give you some polyhedral object. And in fact, that's true. So this is, let's say, this is a baby version of a structure. Here is that prop V is a polyhedral complex. And okay. In a minute, I'm just going to talk about curves. And sort of one of the nice things about these things, well, why would we study this? And if you like combinatorics, this is a very nice object. It's something in discrete geometry, so it's worth studying. But if you're an algebraic geometer, well, why is this relevant, right? So other than remembering the valuations of solutions, what else does it know? Well, there's a theorem by B.D. Groves. So B.D. was the professor here many, many years ago. And so they showed that prop V has, remember something about the original variety. So the dimension of this polyhedral complex is equal to the dimension of your variety. And furthermore, if your variety is irreducible, all the maximal cells will have exactly this dimension. It's going to be a pure polyhedral complex. Questions so far? I have a question. How much time is left? I just don't remember.
I make it 19.
19. Ah, okay. So my watch is working. So we can again tropicalize the solutions and tropicalize our polynomials and find tropical solutions to these tropical polynomials. And the big theorem is that they agree. So this is something that was done by Kapranov in the hypersurface case. Then Spire does Inspire for the table general result about this. So there's a missing characterization here that has to do with initial ideals. I'm not going to need this, so I'm not going to talk about this, but I believe there's a mini talk about this. So there's somebody talking about initial degenerations. Okay, so far, this is what it is. So one feature or a bug that you can think depends on your perspective is that this assignment really is a shadow, right? As we said originally, this is a combinatorial shadow of an algebraic variety. It remembers something, for example, the dimension, but doesn't remember everything. And many objects that are different in algebraic geometry can have the same tropicalization. So the point is that the construction of tropicalization is very sensitive to where my variety is placed, right? So I have my variety in some affine space or a torus defined by a given ideal. If I re-embed, the things might look a bit different. So tropicalization is very sensitive to choices of coordinates. you can think, well, this is great because then, maybe I can make a living out of finding what choices of coordinates for this. So I've done part of that. So, so if you want to learn about this, you can Google spatial topicalizations, and then you'll see more about this stuff. You can say, well, maybe I want to have a coordinate free construction about this. And so there's a result by Champagne that says sort of a universal tropicalization. I'm paraphrasing, but this is the main idea. Let's say coordinate free tropicalization is a known object in analytic geometry. So this is the Berkovich analytification of my variety. Or the space of semi-evaluations on the. And of course, there's a map that sends this universal tropicalization to a given tropicalization, depending on your choice of coordinates. The map is nice, and then of course the question is, how much of my variety can I see, or no, for my given choice of coordinates, how much of my embedded explicitly tropicalization can I see in this kind of funky object over here. So there's a lot to do about this. Of course, if you want to do some enumerative geometry, which is part of what I want to do in part 2, so that also goes bad in some sense, but you have to be able to read the data in the appropriate way. Okay, so let me show you some examples about this. So let's talk about just K star. If I tropicalize my K star, well, I just have to take a point of the series and consider its valuation. Well, I'm just going to get my real one, right? If I want to compactify, I'm going to have a point at infinity, but I'm working in the torus for simplicity. Now, I can also have a different characterization of a line. For example, I can look at the equation of the line 1 plus x plus y equals 0. And this I'm going to look at in the torus. So now if I tropicalize my polynomial, 1 plus x plus y, I'm going to get the max of first entry has valuation 0, then second monomial has only an x, third monomial has a y, and I want to find the corner locus of this object. So the picture that I'm going to get is something that looks like this. It's going to be a tripod, and the vertex just has to be 0, 0. Okay. So if you think about this, well, if y is very large compared to x and it's positive, the max is going to be achieved once, and the value is y. If x and y are negative, the max is 0, so that's going to be my value there for my polynomial. And then on this side, I'm just going to get x, right? So when these things come together, when there's ties, then that's when this becomes interesting. So that's going to be my object. And of course, if you want to look at this theorem or definition from the first perspective, I can say, well, my points have coordinates x and minus 1 minus x. And you can start saying, well, if the valuation of x is positive, this guy will have valuation 0. And so that's going to give me this guy. So this guy will remember x with the valuation of x is positive. This guy will remember when valuation of x is negative. And then this guy over here will look at points where the valuation of x is 0. And so presumably there could be a cancellation of this constant, and you're going to start having t's with powers. Right? So this is sort of the picture. So depending if you work with with this natural embedding, you get a line. Here, this is a tropical, and then you can see how this is going. You go now to 3 dimensions, you're going to have 3, 4 legs, and so on and so forth. So, yeah. And you kind of relate, you can relate these two together, but that's a story for another time. Questions? Okay. So now let's see the second issue is that tropicalization is not injective. Again, different, because I just remember the valuations of the points, I don't know, for example, what's the initial coefficient. So this is something that is forgotten when I do tropicalization. So second thing, tropicalization is not injective. So as I said, if you want to do some questions in enumerative geometry, then you have to be a little bit careful because maybe 2 classical objects that you want to count will have the same tropicalization. So this can be a problem. For a tropical enumerative, let's say enumerative tropical geometry. To be a little bit careful, and I believe Sabrina is going to tell us a little bit more about this prediction. Of course, you can have, even if you still have a finite count, maybe 2 things that you want to count classically tropicalize to the same thing. If you know, sort of with which multiplicity to count these tropical objects so that the count matches, that's good. But of course, the big issue will be if you have an infinite count on that side. Then you have to be a little bit. So if the count is finite, if the tropical count is finite, we can assign, let's say, tropical multiplicities to each object. Match the classical count. Let's say match or rediscover, or maybe discover, maybe even better, a classical count. So this is the framework of correspondence theorems that Sabrina is going to tell us about. And of course, if the count is infinite, let's say the tropical count is infinite, and this is a phenomenon known as we have superabundance of tropical objects. Then we need to be able to recognize what tropical object really actually comes from the classical one. We need to dig deeper. Okay, so this is sort of in the frame of lifting questions. And so that's partly what Titus is going to talk about, and also what I'm going to talk about in the second part. Okay, now let's draw some pictures. So for my, my title said space sextic curves, but we're going to do some reduction in dimension and deal with pictures in the plane. So for the rest, I'm going to talk about plane curves and what tangencies look like, and then I will stop. So. Okay. So this idea that we saw over there of drawing these places where the function is linear and then becomes, and then look for ties between these two linear functions gives you a connection to Newton subdivisions of polygons. So the slogan will be the tropical plane curves are dual to Newton subdivisions of polygons. So let me show you some pictures. Let's draw some pictures over here. So let me work with an example of a conic. So I'm going to take this conic over here, c times x squared plus p times y squared plus xy plus x plus y plus t. So this lives again in my field of Euclid series. That's my polynomials, and over that field, and two variables x and y. And so first thing I'm going to do is I'm going to build the Newton polynomial F. So I'm going to look at all the monomials appearing. So aij, x to the I, y to the j. I'm going to just record the exponent. And then I'm going to take a concept called all exponents. When that actually appears, so I don't want to record the 0, 1. So in this case, I'm going to have, oh, this is a great, that's nice. Okay, so I'm going to have the x squared is going to give me 2x here, then y squared is going over here, xy is give me the 1, 1 point, x gives me 1, 0, y gives me 0, 1, and t gives me the constant, and so that's going to be my life. Okay? Now, this doesn't know anything about the coefficients other than either 0 or not 0. And so I can remember the evaluation of these things and reinvent this. Instead of considering the point by j, I'm just going to consider a point in R3 where the last entry is the negative evaluation of my coefficient. So for the Newton subdivision, so instead I'm going to take the point, or the monomial a ij, xi, yj, and I'm going to record the exponent and then negative of the evaluation of aij. And I'm going to take the convex hull of these guys and look at the upper part. Upper hull, so what I see from above. So let me show you this example. So I'm going to have again my entry 5 points. Now, let's see. So valuations here are going to be 1, so this is negative. This guy has valuation 1, so we get a negative 1. This has valuation 0. This one has valuation 0. That guy also 0, and this has valuation negative 1. So in the picture, these three guys will stay put, but then these guys will go down. And I'm going to draw them one floor below. And when I take the convex hull of these things, well, you're going to see the convex hull here is going to be these 4. So the upper part is going to consist of these triangles. And so what's going to happen is if I project down to R2, they're going to subdivide my nice dilated simplex into smaller simplices. And so the first 3 are going to be in one facet. So we get this one. These 3 are in one facet. That's another triangle. The one in the back is this one, and the one on this side is that. Okay. So I'm going to get we get a subdivision, and this is the Newton subdivision. Okay. So in the tropical picture for the plane curve is the same as the one we did before with the corner locus. It's going to be dual to this Newton subdivision. Now, if I want to talk about smooth objects, so smooth tropical plane curves will correspond to a special subdivision, namely the ones that I have the maximal, well, I have triangulations first of all, and second, I have the maximum number of triangles. So these are going to be what we call unimodular triangulations. Of these Newton functions. Okay, and again, unimodular means syntheses, in this case, of area 1. Okay, so for my conics, I can draw the pictures here. So let's draw some conics. So I'm going to have my dilated simplex. Let me draw a couple of them. So we can subdivide like we did here. So this will be the picture above. So we will get this kind of picture. So the edges are going to be perpendicular to the edges of the subdivision. And then you need to do some calculations to find what's the actual value of the vertex. And now I can start flipping edges around. So I can flip this guy over here. So that will give me another conic. I can flip the vertical one here. So that will give me another conic. That's going to have that. And this is slope 2. Slope 1 under there. And then finally, this one over here, which is sort of symmetric to that one. So I'm going to have this, and then I'm going to have slope 1/2, 1, 0. So those are going to be my prototype for parts. Okay. Okay. So this will be sort of, if you wanted to study different types of subdivisions, you will get moduli of tropical curves with associated to a fixed polytope. So it's associated to some living in some toric variety. So that will be the embedded world. If you want to work in the abstract world, then you have to go to abstract graphs like these, where you have a metric. So that's what Talia is going to focus on. And so for the remaining 5 minutes, let me tell you a little bit about tropical tendencies. And so the question is as follows. So classically, how do we consider tendencies? Well, usually you will have objects that curves, for example, intersecting, and if the intersection multiplicity is 1, the point will be a simple point. And then if these intersection points start to come together, you will get higher multiplicity points, and so that's going to be a tangency, right? So classically, tangency point for us for today will be a point, let's say intersection point, higher multiplicity. And so we can use the same definition to address the question of the definition in the tropical world. So tropically, and use the same definition. But the issue here is that you have to be a little bit careful when you do intersection theory in the tropical world, because tropical intersections can be subtle. Okay, now it's going to scroll to the boards. And so how do we do tropical intersection? Well, let me show you an example with some pictures, so then you see what's the situation, and then we can take a break. Okay, so for example, let's say I take two lines, two tropical lines, and I want to intersect them on my lines we saw earlier. Let's say two tropical lines and R2. So this will be one line, and I have another thing that looks exactly like the same. And so you can have two different situations, something like this, where you have really one intersection point there, and there should be one point. So how do we count the multiplicity here? So the multiplicity is, I'm going to look at the directions of the edges. So I'm going to have -1 for one, and then 0, -1 for the other. I take the determinant and I take the absolute value, so that gives me a 1. Now, maybe I pick my curve, my line to be non-transverse, so maybe they overlap along ray. And so now what do I do here, right? So this will be the set theoretic intersection, but lines should meet at one point, not an infinity later. So how do I go about this? Well, so we can just say, well, let's just move it a little bit. So take, so this place, one of the lines, maybe let me keep the green. That's transverse picture. And then move that. Move the intersection point. The second point, so here, for example, I will get that was my picture. Let me just display it slightly. So now I have this point, and then I move back my point. So this really should be the two intersections. So that will be what we call stable intersection. And so what will be a tropical tangency? Well, let's do an example of a conic and a line. Let me pick, for example, the conic that we've been working with, the one we did before. This conic over, yes.
I have a quick question to
Yeah.
the displacement, because I mean, is there an exact way in which you mean what is there an exact definition of displacing? Because,
Yeah,
for example,
so you take a generic vector of small length, and you do the epsilon times b plus one of the lines, and you intersect with the other one.
Okay.
So that will be this guy over here, and then you go back by taking epsilon going to 0.
But this doesn't give you a unique point, no? Because if I, for example, take the top, if I take the left line and I move it so far to the right that the vertex is to the right of the.
But it's not so far, because
I can't. So
small,
this epsilon is also precisely defined.
Well, small enough.
Well, you also take the limit as
You
epsilon
have
goes
to
to
take a
0.
limit, right? So then
Ah,
I go
okay,
backward
okay,
until
okay,
it equals to
okay.
0. That's what I said. This is not really the, this is how we compute it, but this of course
Yeah.
is not the point.
Okay, so if you take the
original
limit
algorithm.
and then it's well defined.
Right, so you displace and then you move back.
Okay,
Yeah, thank
thank
you.
you.
So for right, okay, maybe this, okay. So maybe this example is not, let me do another one where you see the pictures. So let's go to the last one over there. So I will need to find, how to fit a picture like this in here so that I get a multiplicity 2 intersection point. This has a slope 1/2. So one possibility will be to put a point like this. So this will be a point of intersection multiplicity. Now, another thing I can do is, well, this kind of looks like something that has intersection multiplicity 2 because there will be 2 points of multiplicity 1, right? Of course, it's a different point, so where is the tangency from here? Well, you can imagine, well, these 2 points, thinking of tangencies classically as contact points coming together, well, we can sort of start moving these points towards each other, and they're going to be meeting exactly in the middle, and that's going to be my, this is the true tangency point. Okay, of course, there's a precise way of saying moving these together. So that's the language of chip firing of metric graphs, or linear equivalence of divisors for the people that know a bit more. And so this example says, well, you can understand what the possible tangency look like. The issue here, and with this will end, is the superabundance of, let's say, tropical tangent lines. Because, for example, I can take this line, start moving the vertex up. That's also going to be a tangent line to the same conic at the same point. So I'm going to have infinitely many possible tangent lines to this conic at the given point, and that kind of sounds wrong, right? Because there should be exactly one. So I'm trying to get families of tangency lines, tangent lines. So for this picture over here, I can take this one, I cannot go beyond this point, so I can move it down, but once I hit this vertex, I cannot move it further. But then I will get all these different families, so I have a one-dimensional family of tangent lines through to a given conic at a given point. And so we need a way to say, well, if you do this classically, you take a classical conic, you compute the classical line, you tropicalize the picture, you should get, among this one-dimensional family, exactly one of these is going to come from the classical tangency. Well, the question is which one is it? And so the second part, we're going to try to go beyond this for Sextic, and Heinz is going to do this for not just a conic and a line, but now we're going to get a quartic curve, and I'm going to have a line, and it's going to be tangent at 2 points. And then we're going to see the same kind of how we can move things while remaining